So last week we looked at what's called the natural response of a circuit, which is what happens when you turn off an energy source or remove an energy source. And it's basically the decay as that energy that's stored dissipates over time. So we analyze the situation as we turn off the power source, that we have this exponential decay that we learned about for example, for a current, could also be a voltage, that decays over time. And we learned that the response here is e to the negative t over tau. This is my current here as a function of time, where this parameter tau is the time constant of the circuit. It has units of seconds, and we learned that for a circuit with a capacitor, it's R times C, and for a circuit with an inductor, it's L divided by R. Now this is basically the turn off transient. So the question arises, well, what about let's call it the turn on transient, which is also called the step response, also known as the step response of a circuit. And this would come about when you have, for example, a power supply that maybe goes from 0 volts and then turns on to some kind of fixed value. So if I have like time here and like a voltage of a source and I turn it on, this thing is called a step response, or the behavior of the circuit is called the step response, because we basically have this step in the energy that we're applying. So let's have a look at a scenario where we need to analyze the step response. So we've got here a RL circuit. We have a voltage source that we've collapsed into a Thevenin equivalent. We have a switch that will close at time t equals 0, and then we have an inductor, and we are asked to solve for the current in the inductor for times greater than 0 after the switch will close. So let's have a look at this circuit and build some intuition. So intuitively, we can actually go a long way with kind of the intuition we already have for first order circuits like this. So for example, we know the initial current in this circuit is quite easy to analyze. The initial current is 0. So the initial current, which would be I of, I'm going to write just before the switch closes, so 0 minus, I at 0 minus, is obviously 0 because the switch opens the circuit. Open circuit means no current can flow. And therefore, because inductor current is continuous, we also have that the current just after the switch closes must also be 0. We can evaluate what will be the so-called final current. So this is what happens after steady state conditions have been reached. So the final current, I'm going to write it as I of infinity, meaning like a limit as t goes to infinity. You might also see this written as like I sub f, f for final, so the final current. In order to analyze that, we would replace the inductor with a short circuit. So let's just quickly sketch what this is going to look like. So I have voltage source, I have resistor, and then the inductor just becomes the short circuit, so nothing particularly interesting there, and I just get that really simple circuit. So the current is, by Ohm's law, Vs divided by R. And I would also expect that the transient behavior that kind of transitions between these two things should behave as an exponential. So the transient should, in fact it does, should behave. I will write does behave, the transient will behave, because it actually does, this is truth. Transient will behave as an exponential. In other words, I will have I of t will go as e to the minus t divided by tau, so t divided by time constant. Now, let's analyze this formally and make these things a little bit more precise. So to analyze this circuit here, we're going to use Kirchhoff's voltage law. So starting in the bottom left corner, this is what I will get. It's minus Vs plus IR plus VL is equal to 0. I will substitute VL is equal to L di dt. And I'm using a positive sign here because the current is defined to flow from positive to negative through this inductor voltage, VL, so it's the direction of conventional current, so positive sign in my equation here. So I substitute that in, and what I end up with is the following differential equation. So minus Vs plus IR plus L di dt is equal to 0. And so our question becomes to solve this differential equation. So you can do that by a separation of variables. The actual mathematical proof is in the textbook, so go and have a look at it there in the textbook. But what I will do is kind of go straight to the answer here. So the general solution for this type of step response and for this type of differential equation, general solution is as follows. We will have I of t is equal to a constant which is the final value plus a transient term, and the transient term will be an initial current minus a final current times e to the negative t divided by our time constant. And let's clarify the meaning of these terms. So where IF is the final current, in other words, the steady state conditions after the transient has decayed away. I naught is the initial current, and tau is the time constant. Let's gather a little bit of intuition about how this general equation works. So intuition, and maybe a little way to check whether you have written these parameters in the correct way around. So our intuition here is if we have t equals 0 and I substitute that in, then I will get that I will write I of 0, then I of 0 will be, let's sub it in, so that is I final plus I naught minus I final times e to the 0, and of course e to the 0 is just 1, so I can simplify this, and it basically the brackets just go away, so this gives me IF plus I naught minus IF, and of course my IFs will cancel and I'm just left with I naught. So that's nice, that's correct behavior for t equals 0. We can also say if we have limit as t goes to infinity, then we will have the following. So we will have I of infinity. I'm just writing it like this. I know it should be a limit, but we can just be concise with our notation. So I of infinity will be subbing these things in, I naught minus IF, and this e to the, it's basically going to be e to the minus infinity, which will go to 0. So this whole term here will just vanish, and I'll be left with just the final value. And so that's the desired behavior there as well. So this is the general solution. This works for inductor currents and capacitive voltages. So just change I to V to get the form for a capacitive voltage. Again, the proof of that is in the textbook, so you can just go and have a look there. But you should know this formula, and we're going to, in the next few videos, go through some examples of using it to analyze different circuits. So basically, we'll need to find initial and final values of the current and the time constant and substitute it in, and that gives us our expression for the step response of our circuit.